I'm Michael Koblenz. I'll be presenting Garbage Collection Makes Rust Easier to Use, a randomized controlled trial of the bronze garbage collector. This is joint work with Michelle Mazurek and Michael Hicks at the University of Maryland. We know that memory safety is a significant contributor to the prevalence of security vulnerabilities. C and C++ both allow dereferencing arbitrary pointers. And we know that a large fraction of severe security bugs are due to memory safety problems from projects like Chromium. Rust is a memory-safe language, unlike C and C++. It does this via an ownership mechanism that provides memory safety, at the same time avoiding the runtime cost of a garbage collector. Now, a prior study by Fulton et al. Showed that a large fraction of their survey respondents felt that Rust is harder to learn than other languages. And many of them were concerned about their ability to hire Rust developers. You can see why, right? If Rust is hard to learn, then you want to hire developers who already know it. But those are hard to find because Rust is a relatively new language. A lot of the interviewees felt like some of the biggest challenges are ownership and borrowing. So we were interested in how we could reduce the challenges of learning Rust by making ownership and borrowing easier. If we could make Rust easier to learn, then maybe Rust could be more adoptable. And of course, safe languages only benefit end users if programmers actually use them. So we did an experiment with our new garbage collector. We recruited 333 participants. And we found that people who used bronze spent about a third as much time as traditional Rust users did when they needed multiple aliases to mutable data. Now, let's talk about how Rust works. In Rust, this is from the Rust book, each value has a variable that's called the owner. There's only one owner at a time, and when the owner goes out of scope, the value is dropped. Now, Rust also supports safe references. Each value can have either one mutable reference or any number of immutable references. Now, Rust also has a lifetime mechanism that ensures that anytime a reference exists, it's always valid. So there's always going to be something that the reference actually refers to if the reference is there. Let's look at a little example. Here we have this function foo. And first, what it does is it allocates this string, and S1 is going to be the owner of that string. And then it's going to pass a reference to that string. You see the ampersand operator there indicating that we're taking a reference to the calclen function. Now, what calclen is doing is it's essentially borrowing S via this reference. So you can see S takes this ampersand string reference and computes the length of that string via the reference. Now, notably, S is not a mutable reference. You can tell because there's no mute keyword there in the type of S. And so we can't modify S through the reference. We can't call this push strip method, which would append high, but we can read it. And then the compiler knows that when calclen returns, ownership is returned to the caller. So after the call returns, there are no more outstanding borrows of S1. Therefore, it's safe to deallocate or drop S1 at the end of foo. So you can see how the compiler can automatically manage memory here without the need for a garbage collector. Now, sometimes it's not so straightforward. If you need multiple references to mutable data, you can use two structures provided by the standard library. One is called refcell. This is a container for mutable data. It provides a method called borrowMute, which returns a dynamically checked mutable reference. So the idea here is that instead of checking safety at compile time, we're going to actually do our safety checks at runtime. And what the runtime ensures is that you can't have two mutable references at the same time because that would be unsafe. Now, if you want to have multiple references to the same ref cell, you need to use another structure called RC. This is a reference counted smart pointer, and it supports a clone operation, which returns a new reference. So you can see by using these things together, if you have an RC ref cell T, this is a reference counted mutable storage of type T. Now let's look at an example of how you might need to use interior mutability. Let's say we want to implement something like a mutable graph, right? So we're going to need multiple mutable references to the same values. Here, we're going to try to do that just via two references. So we're going to take two references A and B to this mutable variable Z, and then we're going to try to mutate Z through A and B. But the compiler says, hey, you can't do that. You can't borrow Z as mutable more than once at a time. That's not allowed. On the other hand, in our mutable graph example, we need to do this somehow. So what you can do is you can use this interior mutability mechanism. And notably, this would be allowed in C or Java. But in Rust, even in a single threaded program, this is unsafe because of the compiler optimizations that Rust includes. So if you're using Rust, you need to use an RC ref cell holding this 42 value. You clone it twice So you have two references to the same reference counted object. And then we're going to bar mute it twice, once at a time. And this is okay because before the second bar mute is called, the second bar mute has gone out of scope. You see, we didn't bind it to a variable. It's now out of scope. Therefore, it's allowed to borrow it a second time. Now, you can see how this is challenging. We were interested in making it easier. And in particular, we were interested in making it easier via a garbage collector. The idea is that garbage collection can manage the memory automatically. And the performance cost is small when it's applied judiciously, as we know from the Cyclone project. Now, most code is not performance critical. So the engineering approach that we propose is that people initially use garbage collection. And then when they discover performance critical portions of code, they gradually adopt ownership as needed. Now, this is a prototype. It has associated limitations. It's not thread safe. It defers checking of multiple mutable references to runtime. It only implements collection for particular cases. But the idea is that it's going to trace the heap in order to find live objects, starting from roots. So prior Rust garbage collectors required either manual rooting, the programmer has to say where the roots are via calling a root method, or manually copying references via a clone method, like you might have in RC. And we wanted to make this as easy to use as possible. So instead, we modified the Rust compiler to emit LVM stack maps. And this enables the prototype's runtime to find roots automatically for the cases that are implemented in the prototype. Good, so then we wanted to know whether this helps. So we did a randomized controlled trial with 333 participants in a programming languages class. We started by giving them 4 lectures on Rust. We gave them 2 live coding demos when the students said the tasks were very challenging. We gave them a survey after completing each task so we could understand how much time they had spent and how they felt about their experience. Now you can see there are 2 conditions. There's a traditional condition and a bronze experimental condition. And there are 3 tasks. There's a basics task, which everybody did without the garbage collector. This is kind of an introduction to how to use the syntax of Rust. And then there was an ownership task, which focused on how to use ownership and lifetimes. And then finally, there was a challenging task that required people who were not using bronze to use interior immutability. We're calling this the aliasing task. So people who did the ownership and aliasing tasks, they did versions that were adapted to their version of the study. So people who had the garbage collector did a version for garbage collection. The people who didn't have the garbage collector used an API that was appropriate for traditional Rust. And then to make sure the learning outcomes were the same pertaining to the kind of main learning goals regarding Rust, we made sure that the bronze participants redid the project without using the garbage collector. So they actually had this additional task, which is identical to the last task that the traditional users did. Regarding completion rate, we saw no significant difference in completion rates of the ownership task, but the bronze users were 2.4 times as likely to score 100% on the complicated aliasing task, which required them to use interior immutability. You can see the orange bar here represents the fraction of incomplete tasks. In terms of completion times, the bronze participants finished the aliasing task significantly faster, a median of 4 hours instead of 12 hours. And you can also see that the participants who used bronze had a much smaller standard deviation. Some of the participants who used traditional Rust spent a very long time on the project, up to about 70 hours. However, if you compare the 2 tasks that the traditional participants did to the 3 tasks that the bronze users did, there was no significant difference in total times if you add up the 2 versus the 3. And this is surprising considering that you would expect an extra task to at least require extra time for submitting the task, and that's reading instructions, that sort of thing. So this might suggest that there's some kind of learning benefit to using a garbage collector in the process of learning Rust. Now, for the participants who used the garbage collector, we asked them to what extent they agreed with the statement that garbage collection in Rust makes writing programs easier. We asked the same question after each part, and participants were significantly more likely to think that garbage collection was helpful after doing the assignment than before it. And you can see this is kind of interesting here. If you look at how they felt after doing the basics task, which means they hadn't used the garbage collector at all yet, about 25% of them agreed either somewhat or strongly that the garbage collector was likely to be helpful. But then if you look at their opinion after they had done this complicated aliasing task, more than 3/4 either somewhat or strongly agreed that the garbage collector was helpful. But then what really convinced them that it was especially helpful was when we took it away, right? If you look at the difference in sizes between the yellow bars and the aliasing GC task versus the aliasing no GC task. People were really convinced once we took the garbage collector away that the garbage collector was really helpful and they really wanted it back. On the other hand, we asked them how much they liked Rust and saw no significant difference between conditions, which is surprising, right? If we saved them all of this time, you might expect that they would like Rust better, but in fact, they did not. So we looked at other factors influencing their perceptions of Rust. We asked them how much they liked Rust, but also we asked them about how they felt about how much time they spent compared to how much time they expected to spend. We also asked them how challenging they thought the assignment was, how frustrated they were, and how stressed they were. And we found a stronger correlation between how much they liked Rust and their stress level than between how much they liked Rust and their opinion of how long they spent. So maybe this means that future design should really focus on reducing stress rather than only reducing the time they spend on tasks. We asked them what was most difficult. They said coding with ownership rules and trying to implement mutability in general was just such a headache. It was like someone who combined the worst parts of C and Java. Interior mutability requires that people in the API either manage these reference counted pointers or use dynamic borrowing, whereas the garbage collected references just work. And so they're able to take their experience from Java and use the system relatively naively without having to think about the complicated APIs of these reference counted pointers or dynamic borrowing. One thing we observed is that the error messages sometimes give very low level guidance, and this can be harmful for beginners particularly. Suppose an error message says, hey, please insert ampersand right here in the code. And maybe that helps. But on the other hand, a lot of times it seemed like participants would follow the instructions without actually really understanding why. And so when they encounter a situation where the instruction actually doesn't solve their problem, they can get really stuck and need a lot of help from a TA. So I think it's important to think about the greater implications of error messages that really give fine-grained edit-level feedback to users. In terms of next steps, we're interested in how we can make Rust even easier to use. So we observed students in a Rust course and identified some key opportunities. One pertains to the observation I mentioned about low-level error messages. Maybe we could have a kind of a cognitive tutor kind of system or kind of a model of the user so it could give appropriate error messages and appropriate advice according to the level of understanding that the user has. In general, fixing compiler errors in Rust is a lot like debugging because you really have to understand kind of how the Rust compiler is reasoning about the program. And I think we haven't yet figured out how to teach debugging effectively. So I'm working on a project in which we're observing professional software engineers to try to understand what techniques are most effective for debugging systems so we can teach debugging more effectively. Another problem that we noticed people having is that sometimes students would insert an error, let's say a syntax error in the file, and then they would scroll down somewhere else and then spend a long time working on something else, not realizing that in fact there was a syntax error up there because the syntax error was expressed via a red underline. And once they scrolled away from there, the red underline was hidden. And so they could work for a really long time and concluding that actually they're writing correct code when the code they're writing doesn't type check at all, and they're not getting any error messages because of the syntax error in an unrelated place. So it's really important, I think, to think about IDE designs that make users aware of the status of the feedback that they're getting and the quality of the feedback that they're getting. Finally, and I think this is common to other kinds of programming too, not just in Rust, it's really important to motivate understanding in students rather than cargo culting. So sometimes it's easy for students to look up an example and copy paste it, and sometimes that works. But if the first example doesn't work, and the second example doesn't work, and the third example doesn't work, at some point, students need to really take a step back and try to figure out what's going on. And it could be that for students, a tool could be helpful in reminding them, hey, wait a minute, you've been copy pasting for a while. Maybe you should stop and think about this. In conclusion, garbage collection significantly reduces the architectural burden of ownership for learners in languages like Rust. And garbage collection can enable completion of complex tasks in less time in ownership-based languages. Thank you very much for listening to the talk.